Hello and welcome to our next lesson for vectors and applications. Today we are looking at linear combinations. So you're going to see how to represent linear combinations of vectors and also what they mean in terms of our r squared and r cubed, so our two-dimensional and three-dimensional space. So starting with the two vectors A and B. So A is given in its component form as 1, -2, and B is given as 3, 5. And we're asked to evaluate 3A minus 2B. And you've already seen how we do this. This is just a scalar multiplication, 3 times vector A, and this is -2 times vector B. And we're really adding the scalar multiple of A plus the scalar multiple of B. So 3A is going to give us 3 minus 6. So 3 minus 6. And -2B is going to give us -6 and -10. And if we add these, 3 minus 6 gives us -3, and -6 and -10, that should give us -16. So okay, we have the negative, so -16, there we go. So then this should also be 16, -16. Okay, there we go. So just cancel this whole thing out. Wait. There we go. Okay, so then we really say that this expression here is a linear combination of A and B, so vectors A and B, and it produces the vector -3, -16. Because we're performing some operations, whether it's scalar multiplication or vector addition, and we are getting a final result here. So now let's give a formal definition here. The linear combination of vectors in r squared, and as always, we're going to start with r squared and then expand to r cubed. So for non-collinear vectors u and v, and remember, collinear is when they are parallel, which means there are multiples of each other, so they have the same direction, but it same direction, and if you translate the two vectors, they will be coincident vectors. So these are non-parallel vectors. Then a linear combination of these vectors is given by A times the vector u plus B times the vector v. And A and B are scalars, so they can be any real number here. And this is just a vector addition, but now with the multiples. So possibly a shortened or lengthened version of u and v. And if you draw the parallelogram formed by these two vectors, then the resultant, which is the diagonal of the parallelograms, is going to be this output here. And from last time, when we wrote any position vector AB as combination of the unit vectors I and j, this was really a linear combination of vectors I and j. So we've already been seeing this, but now we're just giving it a formal definition. And why we do that, and the reason it's important, and especially with non-collinear vectors, and just to give you an example, if they were collinear vectors, so if you had 2, 3 plus 4, 6, then this is really 2, 3 plus 2, 2, 3. So this is just 3 times 2, 3. So you don't actually have two different vectors, u and v. It's just the same vector, just multiples of each other. So that's why they have to be non-collinear for you to have two different vectors. And the reason for that is because these help us form spanning sets. So a spanning set for r squared is a set of vectors, and for example, in this case, the unit vectors I and j, that span all of r squared. So what that means is that every vector in r squared can be written uniquely as a linear combination of the two vectors I and j. And we already saw that. Given any component form, we just write, so given a b, we just write a I plus b j. And so we then, based on that, we can say that I and j form a spanning set for r squared. Now, actually, there's an infinite number of two vector sets that can serve as the spanning set for R squared. As long as they are non-collinear vectors, then any two vectors that you pick and put in a set will be a spanning set for R squared, which means that you can choose two coefficients that are two scalars in the set of real numbers, and you can form any other vector in R squared using just those two vectors. So let's see, for example, a couple examples. Starting with the vector 1326, and this is vector x, we're asked to write this as a linear combination of each of these following set of vectors. So we have starting with A, and then I gave you one more for B. And so my point here that I'm going to be proving to you is that this will be a spanning set for R squared, which means that any x that you choose in R squared, you can actually write as a linear combination of these two following the same process that you're going to see here. And if you're not convinced, I suggest you pick any random vector that you want and try it out for yourself. So starting here, we want to find A and B are scalars here. So scalar A and B, such that if you multiply A by -1, 4, which is our first vector, and then B by 2, 5, which is our second vector in the set, then we have a final output of 1326, which was vector x. Now, using scalar multiplication, this is really -A, 4A, and then this is 2B, 5B. So the result is then in our x component, -A plus 2B, and then in the y component, 4A plus 5B, which is exactly what we see here. And so the x component has to be equal to 13, and the y component has to be equal to 26. And that's how we end up with these two equations here. This is just my x component, and number 2 is my y component. Now, this is a system of two equations and two variables, so we actually can solve these. And one method you're going to see is that I'm going to get one, either the A or the B to be equal so that I can do subtraction and solve by elimination. So here, because I have -A, I'm going to multiply this whole equation by 4. And then I will end up with -4A plus 8B equals 52. And remember, it's the whole equation. So all the terms on the left-hand side and on the right-hand side. So now, having this and equation 2 and this one, if you add them, then 4A minus 4A is just going to be 0. And then 5B plus 8B is going to be left. And sorry, so slight error there, but I fixed it for you and it'll be fixed on your updated files as well. But here, when you now add this to this equation, what I forgot to do was also add the right-hand side. So 26 plus 52 will be 78. And so then we are left with 13B, which is equal to 78. So B is really equal to 6 if we just divide by 13. And now, substituting back into equation 1 or 2, you can choose whichever one, you should get the same answer. We want to solve for A. So I just chose 1 because then it's just -A. So -A plus 2 times 6, which is my B value from here, has to be equal to 13. And for this to be true, A has to be equal, or -A has to be equal to 1, which means A is equal to -1. And now we are going to check. And this part is super important in case you also make an error like I did. And had I gotten to this check, I would have seen that my answer would have been incorrect. So then I would have made an adjustment. So let's double check now. So here, -A is going to be -1 plus 2 times 6. And this is 1 plus 12, which is 13. And this matches my right-hand side here as expected. And now in part 2, I hope to get 26. So let's double check that as well. So here, 4 times -1 plus 5 times 6. So we have 30 minus 4, which is 26. And those two both match. So then I have A is -1 and B is 6, and that works. And so I have shown you that I can write the vector x as a linear combination of these two vectors, and these are the two coefficients or the scalar multiples that I have that would satisfy my equation. And again, try any vector yourself. You will get an A and B value. And again, A and B are just scalars in the set of real numbers. They don't have to be friendly numbers. You can even get decimals in there or like fractions in there, and it still works. We do have that it is a linear combination. Now let's try for these two vectors here. Hopefully no mistakes here. So here we want to find A and B such that A times 1, 0, which is my first equation, or sorry, my first vector, and plus B times the second vector, -2, 1, is going to give me 13, 26. So that is, if I multiply the scalars or distribute the scalars into the vector, I have A 0 and then -2b, b. And I end up with A minus 2b and b. But from here, it's really easy to see that b is actually equal to 26 because I don't have any a values here. So really what I'm solving for is A minus 2 times 26, which is 13. And I get that A is equal to 65. And again, they are two scalar values, so then it does make sense that we have a linear combination. But let's double check that to begin with. And what I've done here is just use these two values here, which is what my new equation would have been. So A being 65 minus 2B, which is 26. Then this is just 52. 65 minus 52 is 13, which is what I wanted. And B is just 26. And so this is really 13, 26, or vector x, and that's exactly what I wanted. So, in fact, and this is what I mentioned to you above as well, any pair of non-collinear or non-parallel vectors can be used to form a spanning set in R squared, provided that 0, 0 is not one of the vectors. And one question I could ask you here is why can we not have 0, 0 as one of the vectors, so our zero vector? And I want you to think, if you have a linear combination or a spanning set with that. So let's say you have 2, 3, and 0, 0 as your set. Then if I ask you to form the vector 1, 0, any scalar multiple of 0, 0 is just going to be 0, 0, so the zero vector. So that's actually not going to help you at all. So really, your set is just 2, 3, and from 2, 3, you're not able to get to 1, 0. So then it is not a spanning set because this one isn't really contributing anything. So really, you only have one vector in that set. So it's very important that they have to be non-zero and non-parallel vectors. And this one I already showed you, if they're parallel vectors, how that will look like and why we can't have a spanning set that way either. So here now we're asked to prove that a set of vectors is a spanning set for R squared. Remember, showing that just one vector can be written as a linear combination of the two vectors is not sufficient to make the claim that it is a spanning set for R squared. You have to actually prove that, and the way you prove it is to show for any generic vector, so any general vector, then I have a linear combination using these two. So let's see what that means. If I pick a vector xy, so this is just random, it doesn't have a specific value in R squared, then my claim to you is that I can write xy as a linear combination of -3, -1, and 2, 1. What that means is I can multiply this by scalar a and multiply this by scalar b, and if I add them for a specific a and b in the set of real numbers, then I can achieve the vector x, y. And again, because x, y is general, you will end up with a formula for a and b that will give you any x and y value that you choose. So we set this up as our two equations the same way we did above. So here what I have is -3a and plus 2b, which is equal to my x component. And then here I have -a plus b, which is equal to my y component. So I'm going to follow the same process as above. I want to multiply by a scalar so that I can apply the procedure of elimination. So multiplying the second equation by -3, I end up with 3a minus 3b, which is equal to -3y. And again, don't forget to multiply on the left hand and right hand side. Now, if you look at these two equations, if I add them together, then -3a plus 3a is going to just be 0. So then I am left with 2b minus 3b, and that is equal to just -b. And on the right-hand side, I have x minus 3y. Or if I distribute the negatives, because ultimately we're trying to solve for a and b, so then b is equal to -x plus 3y. So pretty much any vector that I give you with x and y, then if you substitute here -x plus 3y, then you can find that b value there. Now, we will use this and one of these equations to find a. And what I'm going to do is actually I'm going to use the original equation here, -a plus b is equal to y. So -a plus now that b, which is using x and y, is equal to y. And I'm just, again, rearranging to get a term for a. There we go. So a is equal to -x plus 2y. So really, the solution to our system of equations is given by a and b, which is equal to -x plus 2y and -x plus 3y for b, which means that any vector xy that we're given, we can find the values of a and b to write a linear combination using those two vectors from our spanning set. So because the values of x and y are unique, then a and b are also unique. And remember, that's one of the requirements for spanning set as well. We need them to be a unique equation for the linear combination. And so then we can claim that the two vectors that we started with up here, so these two, are a spanning set in R squared. And so here we're asked to, and I encourage you to try it on your own first, but I will show you as well, to use the formulas to write -425, or you can pick a vector of your choosing as a linear combination of the spanning set. So using the formula above, I'm going to find A is -4 plus 2y. So 50 plus 8, 58. And B is, maybe let me write B here. B is going to be -4 plus 3, y is 25. So here we have 75 plus 8, we have 83. Now, and you can try this on your own now, but 58 times -3, -1 plus 83 times 2, 1 should give us -425. So we can try this. Here I would have and then plus 166 and then 83. So -174 and plus 166, or maybe I multiplied incorrectly. It should have been, my bad. I don't know why I added 8 to both of these, and this one should have been also -79, because it's just plus 4, and I don't know where I got 8 from. Um, so then I have to fix these. That's why I was not adding. The math was not mathing. So here we have 54, and then here we have, well, minus 79. Okay, so now 54 times -3, we have 162, and then just -54 there. And then in this part we have, oh my, so many errors. Okay, there we go. That one should have been positive 79. And then we get 158 here, and then 79. So now 162 plus 158 is equal to -4, and then -54 to 79 is 25, and that's exactly what we wanted. We wrote the given vector as a linear combination of the original two vectors, so then we have a spanning set. And again, you can try any vector of your choosing, and you should be able to get values of A and B. Just don't make as many mistakes as I did. And but it's okay. Mistakes are okay. You learn from them. And we have shown that those two vectors are a spanning set. And you can follow the same process for any two vectors that you're given if you're trying to prove their spanning set for R squared. And now let's expand to R cubed. So same thing with R cubed, but now we just have to account for that Z component. So for non-collinear vectors u, v, and w, so again, they're not multiples of each other. A linear combination of these vectors is when you are multiplying them by scalars. So here we have the scalars a, b, c, which are any real number, and you add them up, then you have a linear combination. And in our previous lesson where we had vector OP, and it was given by component form ABC, and we wrote this as AI plus BJ plus CK. This was actually a linear combination of the unit vectors I, J, and K. And now a spanning set for R cubed, similar to above. Now we just have that K vector in there. So the set of vectors I, J, and K, which are the unit vectors, and I hope you see now why they're also called the standard basis vectors. They are set to form a spanning set for R cubed, which means every vector in R cubed can be written uniquely as a linear combination of the three unit vectors I, J, and K. And we already saw how it would just be A, B, and C as our scalar multiples. And similarly, there is an infinite number of three vector sets that can serve as a spanning set or basis for R cubed. And it follows the same process if you're trying to prove that three vectors are a spanning set for R cubed. You have to start with so for example, given A1, B1, C1, C2. So let's say this is our set, and then A3, B3, C3. You would just pick X, Y, Z, and these ones are actually numbers. So I'm just showing you for any random three, but you can try with finding three non-collinear vectors that will be your spanning set, and then this one will be your random one. And what you're trying to show is that A1 plus A2 plus A3 is X, B1 plus B2, B3 is Y, and C1 plus C2 plus C3 is going to be Z. Oh, and actually I forgot one. We have to add in the coefficients there as well. So you do need the multiples here. So coefficient. I know it's a little confusing, but let me do A21, A31. These are the scalar multiples. Or you know what? I'm going to do this L, M, and N as the scalar multiples. There we go. So then this will be L, 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 M, 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 and then N, N, N. And then you have three, and remember your variables are L, M, and N, which are your scalar multiples. Because you are given A1, B1, C1, and A2, B2, C2, A3, B3, C3. So you're really trying to find three scalar multiples that will give you a generic X, Y, and Z. So then you have three equations, three variables. And again, by process of multiplying and subtracting for elimination, you should end up with three equations, L, M, and N, in terms of X, Y, and Z. So these will be in terms of X, Y, and Z, so that any vector X, Y, and Z that you're given, you will be able to find L, M, and N and form a linear combination. So I'm going to show you now just with the unit vectors. So for example, we had the vector 4, 7, -5, and we want to write it as a linear combination of the unit vectors I, J, and K. And we're going to show this geometrically as well. So as a linear combination, remember I is 1, 0, 0. This is I, this is J, and this is K. And so this is 4 times 1, 0, 0, this is 7 times 1, 0, 1, and this is -5 times 0, 0, 1, which gives us 4i plus 7j minus 5k, and this is our linear combination. Now, what that looks like geometrically is on our x-axis, you go to, this has to be all the way. Sorry, the graphics sometimes are a little messed up, but this is 4i, which means we on the x-axis we are at 4, 0, 0, so we haven't moved in the y or z space. Now for j, we are going in the positive direction on the y-axis, so this is 7j and it's 0, 7, 0. And for k, and again, this should also be the whole way, we are going in the negative direction on the z-axis, so we end up at 0, 0, -5. Now, if you connect all of these, and this would have been that rectangular prism formation that we saw, but this would just be our point P, which is 4, 7, -5, and this is the resultant vector there, and it's given by OP, our position vector, starting at the origin. And so, just to put this as a claim, any vector OP and given by ABC can be written as the linear combination of the unit vectors, both in component form and in the unit vector form as such, using just its own components, A, B, and C. Now, a plane is defined as a linear combination via linear combinations as the span of two non-collinear, or again, non-parallel vectors v1 and v2. And it does pass through the origin, and it's expressed as the set of all possible linear combinations. So you're given vector v and v1 and v2. And so a linear combination of them would be a v1 plus v2. And remember, because now we're working in R cubed, it actually isn't sufficient to have v1 and v2. It will not be a spanning set, but it will form a plane. So think of our 3D space, and if you cut any 2D cut in between this 3D space, and this can be, for example, our XY plane that we're familiar with. So thinking back here, our XY plane is just going to be taking X and Y and this two-dimensional space here, then that is a plane. You can also do that with the ZY plane, which will be like a 2D space here, or even the XZ plane, which will be the 2D space there. But really, as we had seen also in our algebraic vectors lesson, you can have a fixed value for either x or either y or either z, and you will form a plane with that constant, which was defined by the equation. For example, if I have the equation x is equal to 4, then that is all of my z and y values with x fixed at 4. And that will actually be a plane, and it will be formed by the unit vectors j and k, and x will just be fixed to be equal to 4. So also, we say that two or more points or vectors that lie on the same plane are said to be coplanar, which means they're on the same plane. And any pair of non-zero, non-collinear vectors that span R2, and if you take those two vectors as a set, they will also span a plane in R cubed. So again, that could just be any fixed value for Z, or you can just have your XY plane. So let's see what that would look like. So here we are given the vectors A and B. And I want you to think already what they have in common. So what's our fixed variable here? And it's actually Z. We can see Z is equal to 1 in both of these. And so thinking in R squared, we would have A is -1, -2, and B is 3, -1. And these two are non-collinear. They're also non-zero. And you can do a quick check for non-collinear because this is not a multiple of this. And so these two will form a spanning set in R squared, but now fixing Z to be 1, they will also form a plane in R cubed where Z is equal to 1. And now we're asked, does the vector C equals -9, -4, and 1 lie on the plane formed by A and B? And already I can check that this is 1, so we're off to a good start. So pretty much we want to find two scalars M and N, so that if we multiply vector A by M and vector B by N, we can end up with vector C. So remember, this is vector C, this is A, and this is B. And now we have three, or the system of equations given by these three equations. So for my X component, I have -m plus 3n, which has to be equal to -9. For Y component, I have -2m minus n is equal to -4. And then for my Z component, I have m plus n, which is equal to 1. Now, adding equations 1 and 3, we actually can do process of elimination there. And I end up with 1 and 3. I end up with 4n, and -9 plus 1 is -8. So then n is just -2. And now from equation 3, I can solve, because m plus n is just 1, then m is equal to 3, so that 3 minus 2 is 1. And I will just check here with equation 2 that this also holds. So then, yes, vector C can be written as a linear combination of A and B, and it does lie on the plane. And if you're fully not convinced, using M is 3 and N is equal to -2, go back to all of these three equations and substitute it, and you should get -9, -4, and 1. And I already showed you for equation 3 this holds. I showed you for equation 2. So really, you're just checking for equation 1. So -3 plus 2 times -3, which is -6, is equal to -9. So there you go. We just checked all three. So we do have a linear combination of A and B, which gives us vector C. And so it is, this point is on the plane, and we do say it is coplanar. And that is the wrap of our lesson on spanning sets and linear combinations. And as always, please check Google Classroom for any additional tasks and complete the practice sets at the end of this document. And don't hesitate to reach out if you have any questions, and I will see you all next class.